Hello dear friends, welcome back to MACSGATE. One second. Yeah. Dear friends, welcome back to MACSGATE. We are learning probability and statistics. So we are doing probability and statistics in three parts. The first part is common for all branches, whereas second and third parts are exclusively for data science and artificial intelligence students. Okay, so in the last session, that is on last Friday, we completed conditional probability. Now we start with the next concept, that is multiplication theorem. Suppose by any chance if you miss the conditional probability, after this session you can go back to the conditional probability session and watch that video also. See, starting from conditional probability till the end of Bayes theorem, these concepts are very important for GATE point of view for all the branches, and especially for data science and artificial intelligence, they are very important. So I'll be doing in a more detailed manner, my dear friends. Okay, so let me start with the multiplication theorem. See, in the last class we discussed about conditional probability. What is conditional probability of B when A is already happened? And that is given by probability of A and B divided by probability of A. Of course, here probability of A should not be equal to 0. That is, A should be a possible event. A cannot be impossible event. Now from this, can you tell me what is probability of A intersection B? So what is probability of A intersection B? It is probability of A into probability of B when A is already happened. Now we also seen this result, that is probability of A given B. According to the formula or according to the conditional probability definition, it is probability of A intersection B upon probability of B. From this we can get the formula for probability of A intersection B, that is probability of A and B, and that is given by probability of B into probability of A when B has already happened. So this is the formula, my dear friends, and this result which we written is what is known as multiplication theorem. This is what we call it as the multiplication theorem. Hope you understand, the idea is clear. So what is multiplication theorem, sir? Probability of A intersection B is equal to probability of A into probability of B when A is already happened. See, my dear friends, how we read it? Probability of B when A is already happened. Simply probability of B given A. We can also define this as probability of B into probability of A when B has already happened. So this is what we call it as multiplication theorem. Actually, for multiplication theorem, it is actually A intersection B, but sometimes they may write in some books, okay, even in most standard books also you can find like Sheldon Ross, okay. Even in many books you can find this particular notation like A intersection B, they simply write it as AB. Okay, so you should understand it as probability of A and B. How you read it, sir? Probability of A and B. So that short notation might be used, so please see the book carefully. Am I clear? So this may be the different notation which generally confuses people, so please be careful. So here the idea is, we are having event A and event B. This is the common portion, A intersection B, and that simply denoted as A and B, and sometimes this notation AB notation may be used. So please be careful. So now I am going to take some very simple but very important examples to understand the concept of multiplication theorem. See, my dear friends, whether you are preparing for regular GATE examination or data science and artificial intelligence, if you understand this, many problems will be very, very easy for you. Even later on when you see the Bayes theorem also. So the entire concepts are linked. So starting from conditional probability, all these concepts are linked. Of course, if you start today's session also, you'll understand. But I suggest you to go back and watch conditional probability also after this session. That is good for health. Right? Actually, the result which we written can be generalized to 3, 4 or 20 events also, my dear friends. So when you generalize that probability of A and B and C. So here we are having 3 events. See, when you are talking about this multiplication theorem, we assume that these events are happening one after the other. So what is probability of happening of A and B and C? That is given by, suppose first A is happening, probability of A into probability of B when A is already happened. After that, now probability of C when A and B already happened. See, actually this order can be changed, my dear friend. It's not necessary that you need to write A, then B, then C. You can first write probability of B, then probability of A when B is already happened, then probability of C when A, B already happened. As I told you, A intersection B might be written as AB. Please note that point. Okay. So you can also write like for probability of C when, okay, or probability of, say, let us take another one, like, you know, B when C is already happened, then probability of A when B, C already happened. So please try to write down all the possibilities, sir. You can write probability of B, then probability of C when B is already happened, then probability of A when B, C already happened. So you can write many forms, my dear friends. It depends on what is the order of the events which already happened. Am I clear? Please note that. Okay. Please note that point, my dear friends. Now let us take one very interesting problem. We try to explore this idea. 2 dice are rolled. So you know, when 2 dice are rolled, what are the total possibilities? When 2 dice are rolled, there are 36 possibilities. Like, you know, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 and so on, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Now the question is, what is the probability that the outcome on the first die is 5 and sum is equal to 8? That is outcome probability that the first outcome on the first die, you can say outcome on first dice is 5 and sum is equal to 8. So for this we are interested in finding probabilities. Outcome on the first die we want 5 and sum is equal to 8. So here you can say A as the event that outcome on the first dice is 5. Outcome on the first dice Can you tell me what is the probability of this event, sir? So when a die is rolled, what is probability that you get 5? When a single dice is rolled, the probability that you get a 5 is 1 by 6. See, generally we assume that the coins or dice which when they don't mention anything, we assume by default they are fair dice. So all the outcomes are equally likely. Is the idea clear? So that is probability of A is 1 by 6. Now, what is that you want? Sum of the outcomes is equal to 6. Sum of outcomes is equal to 8. Okay, sorry, 8. No problem. Sum of the outcomes is equal to 8 when 2 dice are rolled. Okay. Now, what is that you want? Probability that A and B you want. So, if you go for multiplication theorem, what is it? Probability of A and B is probability of getting 5 on the first dice followed by probability of getting sum 8 when outcome on the first dice is 5. See, this is very interesting. See, this probability we know. What is probability of getting 5 on the first dice, sir? That is 1 by 6, you know. Now, what is probability of getting sum 8 when we get 5 on the first dice? See, normally, what is probability that sum is equal to 8, sir? What is probability that sum is equal to 8, sir? Out of 36, there are 5 cases for one. But here, 36 cases does not happen. The outcome on the first dice is fixed. That is, we get 5-1, 5-2, 5-3, 5-4, 5-5 and 5-6. That is only 6 cases favorable. Out of these 6 cases, how many can give you sum is equal to 8? That is, I want sum is equal to 8. I want sum is equal to 8 when outcome on the first dice is 5. That is, when outcome on the first dice is 5 means there are 6 cases. Out of 6 cases, how many cases favorable for sum is equal to 8? Only one case. Only one case favorable for sum is equal to 8. So what is the answer for this, sir? 1 by 36. That is, what is the probability that we get 5 on the first dice and sum is equal to 8? The probability is 1 by 36. See, you can try different problems like this, my dear friends. Maybe I may ask you, like, 6 on first dice and sum is equal to 9. 6 on first dice and sum is equal to 9. See, actually, you can solve this problem directly also. First day you want to get 5 and what is that? Sum is equal to 8 you want. So, out of 36, how many cases favorable for this? 5 on the first day and total is equal to 8. Only one case favorable out of 36. So, directly also you can solve it. But I am using this multiplication theorem so that whenever such problem comes, we can easily analyze the story. Am I clear? Please note that. Now here, 6 on the first dice and sum is equal to 9 means this is what you want. This is one case favorable out of 36 cases. But according to this, if you go, according to this method, if you go, what is it? 6 on the first dice. 6 on the first dice means 1 by 6 cases. Now, out of this 6, because 6 on the first day means 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. In that, you want sum is equal to 9, that is only 6, 3. So, how many cases favorable? 1. So, what is the answer, sir? 1 by 36. You can try different numbers, my dear friends. Sum 10, if you take sum 10, what happens? 6, 4. Like that. So, for all this, that is the idea. So, what we need to understand here, my dear friends, we need to understand that we want A and B to happen. So, when A is already happened, what is the probability that B happens? That is what is called as multiplication theorem. So, what is probability of A and B, Babu? Probability of A already happened. Then what is probability of B when A is already happened? This is the story. Clear? Now, let me take one more question. In a class of 100 students, 60 students like cricket. So, class, there are 100 students, 60 students like cricket and remaining does not like cricket. Okay, they have their own problems. Okay, maybe some Dhoni retired or some kind of things, right? Whatever may be reason, they don't like cricket. Okay, it may be cricket or IPL in particular you want to say, you can say that. Out of 60 students who like cricket, 48 students have sports shoes and 24 students who don't like cricket have sports shoes. See, this is the information given and see the question. Actually, I given series of questions here. What is the probability that a student selected at random like cricket and have sports shoes? So, it's like, total there are 100 students in the class. In the class, there are 100 students. Out of that, 60 like cricket and remaining does not like cricket. So, actually, it is divided into 60-40. Here, there is no other information given and it is not mentioned that there are some people who don't like both. Nothing like. So, we take 60 like cricket and 40 don't like cricket. Out of the 60 people, 48 have sports shoes and remaining how much, sir? 12 students don't have sports. So, they have sports shoes and these people don't have sports shoes. This is like, this entirely cricket, they like it and these people don't like cricket. Now, out of this 40 students, 24 students, that is 24 is around 60%, 24 students are having sports shoe and remaining don't have sports shoe. Remaining means how much? Maybe 16 people. Now this is the information given to you. Now the question is, what is the probability that a student selected at random like cricket and have sports shoes? What is the probability that a student selected at random like cricket and have sports shoes? So what is it? You can directly say 48 out of 100. 48 out of 100. See, this is the situation where he likes cricket and he is having sports shoes. So that is 48. So that is 48%. Suppose if you want to solve this like, probability, like, let us call this as A as the event that student like cricket. And B as the event that student has sports shoes. Or let us make it simply like, you call it as C and you call it as S, because it would be easy for us. Okay, C means what, sir? He likes cricket. C complement means he does not like cricket. S means he is having sports shoes. S complement means he does not have sports shoes. See carefully. Here initially 60%, 60 students, that is out of 100, 60 students means 60%. 60 students like cricket. And how many don't like cricket, sir? 40 students don't like cricket. And out of these 60 students, okay, there is a story like, having sports shoes when they like cricket. So how many students have sports shoes when who likes cricket? 48 students. So this is 48. And who don't have sports shoes when they like cricket? Remaining. That is 12 students. Is that clear? Now what about this? Who don't like cricket and who are having sports shoes? Of course, they can play other games, no? Don't restrict that they should not have sports shoes like that. So what is it? 24 students. This is 24. Am I clear? Now what about this? S complement when C complement. What is it? Obviously 16 people. Now the question is, what is the probability that a student like cricket and is having sports shoes? So you can say like probability that he likes cricket and probability that he is having sports shoes when he likes cricket. Now what about this? He likes cricket means out of 100 it is 60. It is probability means 60 out of 100. Now he is having sports shoe when he is liking cricket. So how many people? 48 out of 60 people. This is like, 60 is the, what do you call the sample space here? Given, because we are finding conditional probability. When like cricket means 60 people only. Out of 60 people, how many like or how many are having sports shoes? 48. So this is the idea. You can cancel these two and you get the answer 0.48, my dear friends. Is the idea clear? So this is what we call it as he likes cricket and he is having sports shoes. Now I can ask you different question like, what is the probability that student like cricket but he does not have sports shoes? So he likes cricket and he does not have sports shoes when he likes cricket. So likes cricket is 60 out of 100. And what about this? He is not having sports shoes. How many? 12 members are not having sports shoes. Okay, out of 60. So that is 0.12, my dear friends. This is 0.12. So he likes cricket and does not have sports shoe is 0.12. Actually, if you see here, this 0.12, because this total is 100, you might be feeling like you got the answer directly. Why you are wasting my time? But if this number is different, things would be different, sir. Please be careful. Okay, here what is cancelling out? This number is cancelling out. But this is 100, because of that directly you are getting answer. Suppose instead of 100 you are having 80 students, 70 students, that values may vary. Please be careful. Here I am giving a simple example. So later on I want you to change these numbers and try. Then you will understand the actual story. Is that clear? Please note that. Now the next one. He does not like cricket and he is having sports. Okay, and not given. And he is having sports shoes. So what is it? He does not like cricket and he is having sports shoe, but he does not like cricket. So how many people does not like cricket, sir? 40 out of 100. Now how many people does not like cricket? 40. Out of that, how many are having sports shoes? 24. So that is 0.24%. And the last one is, what is the probability that student does not like cricket and he does not have sports shoe? So what about this? C complement, probability of S complement given C complement. This is 40 out of 100 and this is 16, 24 gone means 16 remaining, 16 out of 40, which is 0.16. So you can try different numbers, as I told you. Suppose instead of 100 students, you may be having 80 students. Okay, in that case, what happens? Let us see the story. Suppose you are having only 80 students, 60 students. Here it is 60 and here it is 20. Out of 60, 48 likes and remaining how many? Remaining means this is 24 only, na? Sorry, 12. But this 20 we cannot have 24 in that case, because remaining people who does not like cricket is only 20. Let us say 16 here. 16. Okay. Who don't like cricket have sports shoes, and only 4 here. So in this case, what happens to this? Probability of this is S complement, this is S and this is S complement. This is C and this is C complement. What is probability of S intersection C? What is probability of S intersection C? That is 60 by 80. That is probability of C. And probability of S given C. What is probability of S given C, my dear friends? In this case, it is 48 out of 60. So now the numbers are different. Okay. 4 12s, 4 20s, 4 3s, 4 5s, 3 by 5, which is nothing but 0.6. Am I clear? Which is 0.6. So that is 0.6% of this. What is this? 48 out of 60 is how much? Is it 6? It's not 60% now. So that is not the exact case, my dear friends. Here it is 0.48, but here it is 0.6, my dear friends. So if the numbers changes, we need to make some calculations, my dear friends. We need to make some calculations. Is that clear? So you can try with different numbers these problems. These type of questions are very regular, my dear friends. It confuses people a lot. But try to understand, try to fix what is given. Okay, what is the second event? See, these are like, depending events. These are like depending events. The second event depends on the first event. Okay, in such cases, we need to take care of what is happened and what is happening now. And what is the probability of the second event when the first event is already happened. So we need to take care of all these things carefully, my dear friends, to solve it. Please note this. Hope you understand. This was a GATE question, very simple one. An examination consists of 2 papers, paper 1 and paper 2. Okay, very good. 2 papers are there. Probability of failing in paper 1 is 0.3. So probability of failing in paper 1. So let us call it as failing in paper 1 as F1 is how much? 0.3. And that in paper 2 is 0.2. That is probability of failing in paper 2 is 0.2. So I am calling it as F1 as probability of failing, or failing in event as F1 is the event which says that failing in first paper, and F2 is the event that failing in second paper. I just define the 2 events. Now, given that student has failed in paper 2, see, some people only read up to that. So you have to read carefully, properly. See, in conditional probability, you need to understand what is the conditional probability. That is, what is A and what is B. A given B or B given A is given. You need to understand that carefully. That is what is already happened and what is happening now. We should understand carefully. Given that a student has failed in paper 2, that is, it is happened. He failed in paper 2. The probability of failing in paper 1 is 0.6. See, given that student has failed in paper 2, the probability of failing in paper 1 is 0.6. See, generally what happens? Sometimes people use their brain instead of what information is given. So generally what happens? We write papers, first we fail in first paper, then we fail in second paper. Like that they use their general knowledge. It is not about what is your general knowledge, sir. Okay, maybe you written the two papers, corrections of the second paper happened first, then correction of first paper might happen. So don't worry about it. Or you got the result of second paper first, then you got the result of first paper. Okay, or you write two different papers where the result of second paper is declared first, then the result of first paper is declared. It's like that. You write ISRO BARC examination. Okay, first you return ISRO, then you return BARC. First results of BARC come out, then results of ISRO coming out, like that. So please read the question carefully. See what happens, this is very important. In the problem, probability of failing in paper 1 is clearly given as 0.3. Probability of failing in paper 2 is clearly given as 0.2. And probability of failing in paper 1 when it is already known that the person is failed in paper 2 is 0.6. That is, given that student has failed in paper 2, that is already happened, probability of failing in paper 1 is 0.6. Now the question is, what is the probability that student failing in both the papers, that is fails in paper 1 and paper 2? If you use conditional multiplication theorem, because what is declared first? F2 declared first. So because we are having F1 given F2, so what is this conditional probability formula we are going to use? We use probability of F2 into probability of F1 given F2. F2 is 0.2. F1 given F2 is 0.6. So what is the answer, sir? 0.12. That is the probability. So what is the probability that student failing in both the papers? 0.12. Very less probability, sir. So hopefully student get good marks and he get very good grade. Okay, that is the idea. Now if you observe in this problem, there is no requirement of this information. There is no requirement of this information. Then why it is given? So as I told you, people use their general knowledge sometimes. People use their general knowledge. So instead of taking F1 given F2, if you taking it as F2 given F1, then what happens? F2 given F1, then what happens? Okay, suppose if you take it as F2 given F1, then what is F1 intersection F2? This is probability of F1 into probability of F2 given F1, which is 0.3 into 0.6, which is 0.18. And if you see, there is the option 0.18 also available, but that is not correct option, Babu. So this is the wrong procedure. So he want you to do this mistake. Am I clear? It is called a trap. Please be careful. Read the question carefully. Am I clear? Whenever you talk about multiplication theorem or conditional probability, understanding the conditional probabilities is very important. What is already happened and what is happening now. So that because of this, I ask students who are not watched the conditional probability video, after this session you can go and watch conditional probability also. You'll understand things properly. Got it? There's one very interesting question. P and Q are considering to apply for a job. Okay, very good. The probability that P applies for the job is 1/4. So let me write down. Probability that P applies for a job is 1/4. Now probability that P applies for a job given that Q applies for the job. Probability that P applies for the job given that Q applies for the job is 1/2. Probability that Q applies for the job given that P applies for the job. Probability that Q applies for the job given that P applies for the job is 1/3. Then the probability that P does not apply for the job given that Q does not apply for the job is what? So the question is, what is the probability that P does not apply for the job given that Q does not apply for the job is what? This is the question. A very interesting question, sir. Very popular question. Okay. All of you able to follow? Right? Now what is the answer for this? Let us try to understand. Now my dear friends, if you observe this conditional probabilities, probability of P given Q. What is probability of P given Q? Probability of P intersection Q by probability of Q. But this is useless because you don't know what is probability of P intersection Q. You don't know what is probability of Q. So this is useless for now. So let us consider this now. What is probability of Q given P? It is given as 1 by 3. But by definition, what is probability of Q given P, sir? It is probability of Q intersection P या तो probability of P intersection Q upon probability of P, which is equal to 1 by 3. But you already know what is probability of P, which is 1 by 4. Substituting this, what happens? Probability of P intersection Q is equal to probability of P into 1 by 3. Probability of P is 1 by 4 into 1 by 3, which is 1 by 12. So now you know what is probability of P intersection Q, which is 1 by 12. Now we know probability of P intersection Q. Now make use of this. Now make use of this. So the question is, what is probability of P given Q? Of course, it is given as 1 by 2, but it is probability of P intersection Q by probability of Q, which is 1 by 2. In this probability of P intersection Q, you know, which is 1 by 12. Okay. And what I do, I'll send P of Q to that side and 2 to this side. Cross multiplication. So this is multiplied with 2. So you get probability of Q is equal to how much? 1 by 6. So once you know all the probabilities, of course you can use Venn diagram, or you can continue with this method like probability of P complement intersection Q complement is, you know, if you want you can use this formula. What is probability of P complement intersection Q complement, sir? Which is nothing but 1 minus probability of P union Q. And what is probability of P in Q? Probability of P plus probability of Q minus probability of P intersection Q. That way also you can try. Okay. From this you get probability of P complement intersection Q complement, and from this you get probability of Q complement. What is probability of Q complement, sir? 1 minus 1 by 6, which is 5 by 6. So this gives you probability of P complement intersection Q complement, and this gives you probability of Q complement. So what is the formula, sir? Probability of P complement intersection Q complement by probability of Q complement. So with this you can get the required answer, my difference. For that you need to apply this formula. So what is probability of P complement intersection Q complement, which is 1 minus probability of P union Q is nothing but probability of P plus probability of Q, which is 1 by 6, minus probability of P intersection Q, which is 1 by 12. So when you simplify this, it is 1. So LCM is 12. 3 plus 2, 5 minus 1, 4. 4 by 12. That is nothing but 1 by 3. 1 minus 1 by 3 is nothing but, correct only, 1 by 3. That is 2 by 3. So this is 2 by 3. And this is 5 by 6. So you can get the formula, sir, 2 by 3 upon 5 by 6. So that is 2 by 3 into 6 by 5. 3 2s and 4 by 5 is the required answer. So what is the required answer, sir? 4 by 5. Or you can use this Venn diagram as I told you. Only two events. P is there, Q is there. So P is 1 by 4, and just now you know 1 by 12 it is. So 1 by 12 means what? 1 by 4 minus 1 by 12 means what, sir? 3 by 12 minus 1 by 12, 2 by 12. And this is Q. Q is nothing but what? 1 by 6. Or you can write 2 by 12 also. 1 by 6 I can write it as 2 by 12. So this will give you how much, sir? Correct only, no? 5 by 12. Okay. So 7 by 12 outside. Is that? Oh, sorry. Q. Sorry. Q totally is 1 by 2 by 12. Then this portion is only 1 by 12. Now Q is 1 by 2 by 12. So this portion is 2 by 12 minus 1 by 12 is 1 by 12. This only B portion. So this is 4 by 12. So outside portion would be 8 by 12. So that is probability of P complement intersection Q complement. So what is probability of P complement intersection Q complement? 8 by 12, which is nothing but 2 by 3. 4 2s, 4 3s. And what about probability of Q complement? From this probability of Q, you know 1 by 6 means probability of Q complement is 5 by 6. From that also you can get like 2 by 3 by 5 by 6. Either you can use Venn diagram or you can use the formula method, my difference. Still you can get the answer for this. The next one. Now, before moving on to the next one, what I try to do is, I'll try to explain the concept of independent and dependent event. This plays very important role, my dear friends. So today we'll try to understand this independent dependent events, and tomorrow we'll try to take up extra problems also, problems on dependent and independent events, problems on dependent and independent events. Okay, so let us continue. Yeah, one second. For this I taken this simple very interesting example, sir. You all know about chords, sir. So if you do not know about chords, let me quickly tell you about chords. There are totally 52 chords which are divided into 4 shoots. Spade and club are black in color. Diamond and heart are red in color. In each shoot we are having ace, numbers 2 to 10, and we are having face cards jack, queen, king, jack, queen, king. This is the story. So each shoot is having 13 cards, total is 52, and there are no jokers in mathematics. Wonderful. Now from pack of 52 cards, suppose a card is drawn. From a pack of 52 you taken a card. Now consider the following two situations. In the first situation, the card is replaced. You placed it back. Okay. Then a second card is drawn. Now I'll ask you one question here before moving to the second situation. Here we taken a card, we replaced it, again we taken a second card. Now the question here is, what is the probability that we get a king in second draw given that we get a king in the first draw? This is my question. That is, you taken a card, you replaced, again you taken a second card. The question is, what is the probability that the second one is a king given that the first one is also a king? See, my dear friend, when the first one is king, you already replaced it. So you are again having 52 cards in your hand. Okay, actually for the first card is king is 1 by 52, but that card is replaced. Now what is the probability of getting second card is king when the first card is also king? It does not matter because you already replaced. You are having all the 52 cards with you. So probability that the second card is king given that the first card is king is still 1 by 52, because it does not matter what is the first card because it is already replaced. Suppose if I ask another question like, what is probability of getting king in the second card when it is not king in the first card? Maybe some other card other than king, not king in the first card. Then what is the probability? What is this probability? Even this is 1 by 52, because even if it is not a king, it may be some other card, maybe ace, but you replaced it. So you are having all the 52 cards. What is probability of taking king in the second draw? It is 1 by 52. So when the second draw does not depend on the first draw, in other words, if the second event does not depend on the first event, then probability of second event given probability of the first event is exactly same as probability of second event. I can directly write it as probability of second event, because first event does not affect the second event. Here these events called independent events. Here these events are called independent events because happening of the first event does not affect happening of the second event. Such events are called independent events, and in such case probability of drawing king in the second draw is directly found. We can find it directly, 1 by 52, and these events here are called independent events. Now consider the alternative situation where you taken a card, a card is drawn from a pack of 52 cards and it is not replaced. You not replace that card. Now the question is, if the second card is drawn, I am asking same questions once again, sir. But in this situation, what is the probability that you get a king in second draw when you get king in the first draw? Again, I ask, what is the probability that you get a king in second draw when you not drawn king in the first draw? So this is the question, my dear friends. This is the question. So here what happened? In the first card or in the first draw, you taken a king. So what is the probability for that? King in the first draw, it is 1 by 52. Not king in the first draw. How many are favorable for king in the first draw? Sorry, I written wrongly, sir. It is, I made a blunder. No one written anything. How many kings are there, sir? 4 kings, na? I written 1 by 52. Not one card, na? 4. 4 kings are there, no? How many kings are there? How many kings are there, sir? 4 kings, na? Kings how many? 4. I written 1 by 52. No one said anything. Okay, sorry for that. It is 4 out of 52. Here also it is 4 out of 52. Here also it is 4 out of 52. Sorry for that. Am I clear? Now, what is the probability that you get a king in the first draw? 4 favorable out of 52. And what is the probability that you will not get a king in the first draw? How many are favorable, sir? 48 favorable out of 52. Now it is not replaced. The drawn card is thrown somewhere. The drawn card is thrown somewhere. Now the question is, if the second card is drawn, what is the probability that the second card is king when the first card is also king? See, because the first card drawn is a king and it is thrown. How many cards you are having? We are having only 51 cards. Out of 51 cards, how many are kings? Because out of 4 kings, one is already gone. How many kings left? Only 3 kings left. Only 3 kings left. Is that clear? Now what about this? What is probability of getting king in the second draw when it is not king in the first draw? Of course, the card is not replaced, it is thrown. So we are having 51 cards now. How many cards remaining? How many king cards remaining? How many kings are remaining? All the 4 kings are very much available because the first card is not a king, some other card. So how many kings available? 4 by 51. 4 by 51. Is this idea clear, sir? So what is probability of getting king in the second draw depends on what is already done. Okay, here these events becomes dependent events. These events becomes dependent events because one affect the other. Am I clear? So please note that. So when cards are drawn with replacement, they are independent events, and when cards are drawn without replacement, what is happened in the first draw definitely affect what happened in the second draw. It subsequently affect the next draws also. So the events becomes dependent events. Please note this point. Now generally I ask this question. If you know, you can answer this. Head and tail are dependent or independent? So when I ask this question, I also ask, they are independent, one option. They are dependent, one option. Option C, it cannot be answered. The question is wrong question, or the information is not sufficient. See, my dear friends, suppose you take a coin, you toss it. You take a coin and toss it. Suppose you get heads in the toss. Can you get tails? So a coin is tossed. If you get head, can you get tail? Given that you got head in the toss, can you get tail? It would be 0 because the tail depends on head. Okay. If you get tail, can you get, what is the probability of getting tail in the same toss? 1. So here head and tail, of course tail is not useful here, but head and tail and head you need to understand. If it is tail, can you get head? No. So here they depend on each other. In a single toss, head and tail are obviously, because head happens then tail cannot happen, tail happens then head cannot happen. That is, they are affecting one another. So they are dependent. See my dear friends, generally people always ask me, sir, the events are dependent or events are independent. I can create a situation where the same events are dependent. I can create another situation where same events are independent also. See, dependency or independency of the events depends on the situation. For example, a single coin is tossed, in that head and tail are dependent. Suppose two coins are tossed. Two coins are tossed. Probability of getting tail in the second toss given head in the first toss. Because whether it is head in the first toss or not does not affect tail in the second toss. So here it is 1/2, assuming the coin is fair. So here the two events, head and tail, are independent. It depends, my dear friends. So dependency and independency depends on the situation. You can't directly blindly say events are dependent, events are independent. Generally, whenever I ask head and tail are dependent, independent, most of the people say they are independent. Here they are dependent, here they are independent. So that question is a wrong question, because I need to tell you whether the events are happening in the same toss or different tosses. Okay, we need to mention that, because that affects, or that particular information tells you the events are dependent or independent. So we need to understand that. Okay. Now, when the events are independent, just now we seen, suppose A and B are independent. Suppose A, B are independent. And if I ask what is probability of A given B? For example, what is probability of king in second draw when you get king in the first draw when the card is replaced? This is simply same as probability of drawing king in the second draw, which is 4/52. Directly you can answer the question, my dear friends. Hope you understand. So here the effect of B is ignored. So probability of A when B is already happened is same as probability of A. So whenever the events are independent, probability of A given B is same as probability of A, and probability of B given A is same as probability of B. And one more important thing is, what happens to probability of A intersection B? We write like, probability of A into probability of B given A. But what is probability of B given A when the events are independent? It is simply probability of B. So whenever the events are independent, probability of A and B is simply probability of their products. That is very, very important result. This is one of the important result, my dear friends. So if A and B are independent, probability of A given B is probability of A, probability of B given A is probability of B, and probability of A and B is simply probability of A into probability of B. Not only that, not only this, we also have some more important results. See, if A, B are independent, not only A, B, sir, even their complements are also independent. That is, happening or non-happening of one event does not affect happening or non-happening of the other event. Then the events are said to be independent. So what is the definition of independent events, sir? Two events, A and B, are said to be independent if happening or non-happening of one event, say let us say one event, does not affect happening or non-happening of another event. Not only happening does not affect happening of the other, sir. Non-happening of A does not affect happening of B. Non-happening of A does not affect non-happening of B. Happening of A does not affect B. Happening of A does not affect non-happening of B. So, not only A, B are independent. Not only A, B, sir. A, B complement are also independent. A complement B are also independent. A complement B complement are also independent. That is, happening or non-happening of one event does not affect happening or non-happening of the other event. So we are having the following results. If two events A and B are independent, A complement intersection B, non-happening of A and happening of B is simply probability of A complement into probability of B when the events are independent. Probability of A and B complement, they are also independent. A complement and B complement are also independent. So all these fellows are independent. All these combinations are independent. So we are having this result. Okay. And when the events, suppose here I just had 2 events, but you may have 3 events, 4 events. Suppose when you are having n events which are independent, then we can generalize the result. Probability of A1, actually it is like, A1 intersection, A2 intersection and so on, AN. As I told you, we can use this short notation like probability of A1 into A2 into and so on, AN. That is probability of A1 and A2 and so on, A. That is simply probability of the product. Whenever the events are independent, probability of their intersection is product of their probabilities. Probability of their intersection is product of their probabilities. Please note this point, my dear friends. Is the idea clear? Now look at this simple examples. What is the probability of getting 8 tails in a row in 8 tosses of a fair coin? So how many times you are tossing a coin, sir? Coin is tossed 8 times. 1, 2, 3, 4, 5, 6, 7, 8. So what is the favorable situation, Babu? What is that you want? What is that you want? You want 8 tails in a row of 8 tosses. So you want tail in the first toss, tail in the second toss, tail in the third toss, tail in the fourth toss, tail in the fifth toss, tail in the sixth toss, tail in the seventh toss, and tail in the 8th toss. So what about the probability? What about the probability? Okay, so let us see this. So what is probability assuming the fair coin? Okay, fair coin means probability of head and tail is same. So what is probability of tail in the first toss, sir? 1 by 2. Given this, what is probability of tail in the second toss? Because head and tail or tail and tail in the different toss are independent. All these tosses are independent. Okay, all these tosses are independent. So probability of getting head and tail in one toss is independent of probability of getting head and tail in other toss. So they are all independent events. So probability of getting tail in the second toss does not affected by tail in the first toss. So what is probability of getting tail in the second toss? It is also 1 by 2. Probability of tail in the third toss 1 by 2. Tail in the fourth toss 1 by 2. Tail in the fifth toss 1 by 2. Sixth toss 1 by 2. Seventh toss 1 by 2. Eighth toss 1 by 2. So 1 by 2, 1 by 2, 1 by 2, how many times? 8 times. So what is the probability, Babu? 1 by 2 whole power 8. Okay, it's like, actually probability of tail in first toss, tail in second toss, and so on, tail in 8th toss. Because they are all independent, so it is simply probability of tail in first toss, probability of tail in second toss, and so on, probability of tail in 8th toss. Instead of writing like this, we are just showing it like, favorable situation and finding the probabilities. So for this event, what is the probability? Okay, all these probabilities are multiplied and you get the answer 1 by 2 power 8. Is the idea clear? Next one. Okay, that is the situation. Of course, I already shown this. Fine. A two-faced fair coin has its faces designated as head and tail. Sometimes more information is given. You just need to understand that. This coin is tossed 3 times in succession. So this coin is tossed how many times? 3 times. 1, 2, 3. To record the following outcomes. So what are the outcomes? Are head, head, head. So first time head, second time head, 3 times you tossed, and you got head, head, head. If the coin is tossed one more time, the probability of obtaining head again, given that the previous realizations of head, head, and head would be what? So if you toss fourth time, what is the probability of getting head in the fourth toss, given that you get head in the first toss, head in the second toss, and head in the third toss? See, it is not about asking probability of this event. People misunderstand. It is not about asking probability of the 4 events. It is just probability of 4th event when you already know the situation. This is conditional probability question. So what is probability of getting head in the 4th toss when you already know that head in first toss, head in second toss, head in third toss? And that is only 1 by 2. Point. So that is the answer. Is the idea clear? Generally people do mistake in this also, my dear friends. I know some people write 1 by 2 power 4. That is 1 by 16 they write. Please be careful, that is wrong. A coin is tossed 5 times. Very good. What is the probability that only first 2 tosses yields head? So you tossed the coin how many times, Babu? 5 times. And what is the favorable situation you want? What is the favorable situation you want? Only first 2 tosses yield heads. So first 2 tosses you want to get heads. What does it mean? In the remaining tosses you get tail. So he wants you to get head in the first toss, head in the second toss, tail in the third toss, tail in the fourth toss, and tail in the fifth toss. And for this he is asking probability. Okay, what is the probability that? Probability of this event. And these are all independent, so you can directly head in the first toss 1 by 2. They are all independent. So simply find probabilities, multiply to get the answer. 1 by 2, 1 by 2, 1 by 2. So what is the answer, Babu? 1 by 2 power 5, which is 1 by 32. Am I clear? So that is the answer. So that is the situation. Only heads in the first 2 tosses, and the remaining remaining tosses you want to get the tail. That is it. Fixed event. Now look here, a card is drawn from pack of 52 cards and replaced. The card is replaced. Very good. If this process is repeated 4 times, then what is the probability of getting king in the 4th draw? What is the probability of getting king in the 4th draw? See, because the card is replaced, does it depend on the previous draws? Does it depend on the previous draws? It does not depend. So probability of getting king in the 4th draw does not depend on the previous draws. What happened in the first draw, what happened in the second draw, because they does not affect the outcome on the 4th draw. So it is simply probability of king in the 4th draw. Total how many? 52. Out of 52, how many are kings? Because all the kings are very much available. So 4 by 52. That is 1 by 13. Is the idea clear? Very good. You want king. Now, this is a very, very interesting and important question. Okay. I want people to understand this question because one of the very, very important questions. Okay, actually it looks a very innocent problem, but I'll be exploring this problem completely. Okay, here only one question asked, but I'll show you how many different types of questions they can ask you. And what is very important is when the events are independent, whether you are having 2 events, 3 events, 300 events, and even when you are having infinitely many events also, you can easily handle them. Tomorrow we'll take up the problems on independent and dependent events, then we try to explore that more. But today this is the last problem where we try to explore this properly. One of the important question. Very, very important. Different variations which I am going to show you now can be asked in examination. Probability of solving a problem by 3 students x, y and z are 0.5, 0.7 and 0.8 respectively. That is, probability that x solve the problem is 0.5. Probability that y solve the problem is 0.7. And probability that z solve the problem is 0.8 respectively. Assuming that they solve problem independently. See, generally also, if it is not given, whenever in such situations, if no other information is given, we generally take our common sense in such cases that people solve them independently. See, independently, generally they may not mention it. Dependently, they have to mention, and dependent probabilities are to be mentioned. Please note that. Am I clear? So, assuming that they solve the problem independently. Suppose I am having a problem, I am unable to solve it. So, I call 3 best students and given them, okay, and I know what is the probability this fellow solve, okay, how much efficiency this fellow is having, how much efficiency this fellow is having. So, when I given that, what is the probability that the problem is solved? The question is, what is the probability that the problem is solved? When the problem is solved, my dear friends, I given it to 3 students. When you say the problem is solved, see, if x is solved alone, no one else solved, then also problem is solved. Y alone solved, then also problem is solved. Z alone solved, then also problem is solved. If x and y solved, but z are not able to solve, then also problem is solved. That is, if at least one of them solve the problem, then the problem is solved. That is, what is the probability that the problem is solved? That is probability that at least one solve the problem. At least one of them solve the problem. What do you mean by at least one of them, sir? X union Y union Z. But we are having this indirect principle, the inclusion exclusion principle for none. You know, probability of x complement intersection y complement intersection z complement is 1 minus probability of x union y union z. So, what is probability of x union y union z? Which is 1 minus probability of neither x solved nor y solved nor z solved. That is, probability of at least one solved is nothing but 1 minus probability none solved the problem. None is x complement intersection y complement intersection z complement. But here they are independent events. Here they are independent events. So, what is probability of x complement intersection y complement intersection z complement? It is simply probability of x complement into probability of y complement into probability of z complement. And you know probability of x by z? I can find x complement, which is 1 minus probability of x, which is nothing but 1 minus 0.5, yani 0.5. Similarly, what is probability of y complement? 1 minus 0.7, which is 0.3. And what is probability of z complement, which is 1 minus 0.8, yani 0.2. So, it is 1 minus probability of x complement is 0.5, probability of y complement is 0.3, probability of z complement is 0.2. Okay. So, it is how much, sir? 1 minus 1530, 0.03. That is 0.97. The probability that the problem is solved is 0.97. So, when I give, or when I am having 3 or more good students, the problem is obviously solved because at least one of them may solve it. Okay. So, in a group, you get more strength. That is the probability. Is the idea clear, sir? 0.97 is the probability. Okay. So, here actually we can create this particular situation where this is the universal set. So, how many students we do not know. What is the total probability? You know, 1, x solving, y solving and z solving. X, y and z. Probability of x solving is 0.5, y solving is 0.7, z solving is 0.8. Now, when the events are independent, okay, the advantage is probability of intersection is probability of their product. See, here this portion is x, y and z. So, what about the probability, sir? What about probability, sir? just multiply probability of x into y into z, that is 0.5 into 0.8 into 0.7 or point, let us write in the order only. What happened to this? Is it not working? One second. So it is x intersection y intersection z, that is 0.5 into 0.7 into 0.8. Okay. So what happens? 7 8s 56. 56 into 5. Half of 560. 5 6 30 25 28 280. So 3 decimals, 0.28 is the answer here. Okay, you just need to multiply the probabilities, my dear friends. And what about this? Here x, y present but z is absent. So what happens? 0.5 into 0.7, complement of this, which is 0.2. This is 0.8 actually. So when you multiply, it happens 14. 14 means 14 fives, 70. 0.07. And what about this? Here x present, y absent and z absent, which is nothing but 0.5 into 0.3 into 0.2. Okay, so which is 0.03. What about this? Here x, y, z, only y present. Out of x, y, z, only y present, x and z are absent. So what about the probability? Very good evening, sir. Very, very good evening. How are you doing? So x complement is 0.5, y is 0.7 and z is 0.2. So again it is 0.07. And what about this portion, sir? Here xz present, y is absent. So it is 0.5 into 0.3 into 0.8, 0.12. And what about this? In this place we are having x absent but y and z are present, that is 0.5 into 0.7 into 0.8, which is nothing but 0.28. And in this only z is present, x is absent, y is absent and z is present. So what is probability for this? 0.5 into 0.3 into 0.8, 0.12. So if you add all of them, you get the required probability. And what about the outside? None of them present. That is 0.5 into 0.3 into 0.2, 0.03. So if you add all of them, you are going to get the required answer, my dear friend, that is 1. Okay, it is 0.28, 0.28 is 0.56, okay, 0.56, then 0.66, 0.68, 0.78, 0.9, somewhere something is wrong. Total probability should be 1 now. Where it is gone wrong? Please verify the answer, sir. Total answer should be 1 somewhere. It is 0.7. I missed 1. 0.7. 1 you are going to get total probability. 0.56, 0.66, 0.68, 0.78, 0.9, 1 probability. Total probability is 1. So you get all the probabilities, sir. This is 0.03 probability. This is 0.07. This is again 0.07. This is 0.12. This is 0.28. This is again 0.28. This is 0.12. And this is 0.03. See, once you write these probabilities, any question can be answered very easily. Suppose if I ask what is probability that at least one solved, Of course, we solve it using formula also. At least one solve means x union y union z. If you want, you can use the formula like, probability of x plus probability of y plus probability of z minus probability of x intersection y, probability of y intersection z minus probability of x intersection z plus probability of x and y and z. That you can write and you can get the answer, my friends. Please note. Or you can do it indirectly like 1 minus probability of x complement intersection y complement intersection z complement, which is nothing but 0.03, which is 0.97. As I told you, you can ask many more questions. See, once you have all the probabilities, I can ask you only x solve the problem, which is 0.03. I can ask exactly one solved. Exactly one means only x or only y or only z, which is nothing but 0.03 plus 0.07 plus 0.12, which is nothing but 0.22. So many such questions can be answered very easily. Exactly 2 means these portions, sir. Exactly means 2 means these portions. That is 0.07 plus 0.12 plus 0.28. That is 0.47. Like that. At least one we already solved it. At least one we already solved it. I am not solving. At least 2 means 2 or more. So this is what you call it as 2 or more, all the 3. So you get all this sums, sir. 0.07 plus 0.12 plus 0.28 plus 0.28, which is nothing but 0.56, 58, 68, 0.75. Okay. At most 1. At most 1 means 1 or less. 1 or 0. So that is nothing but 0.03, 0.07, 0.12 plus 0.03. 0.25. At most 2 or less. 2, 1, 0. You can do it like 1 minus all 3. That is 1 minus 0.28, which gives you the required answer, my dear friends, which is 0.72. Is 0.72. See, once you understand this idea, many such problems can be easily answered. Okay, suppose if I asked, what is the probability that x and y solved? See, when I say x and y solved, z may be involved or z also may be involved, sir. So I am just talking about this. If I say only x and y solved, x and y solved, please try to understand the difference. Probability that x and y solved. Probability that x and y solve the problem. And what is the probability that only x and y solved? That is, y does not involve. So x and y solved means 0.7, 0.07 and 0.28, that is 0.35. Probability that only x and y solved is 0.07. Is that clear? So that is the idea, my dear friends. Okay. And before moving, before closing this session, actually, that is before actually stopping today's session here, I just introduce one simple idea. I already told you, but again, I just want to make it very, very clear, because this is very important for tomorrow's session. Okay. Biased, unbiased. Okay. Unbiased, bias. So sometimes for bias, they also call it as loaded. See, generally the events we talk about, okay, unbiased events, biased events. Or when you talk about a coin, they generally say unbiased coin. Okay, like unbiased, they also call it as fair. See, what do you mean by unbiased and what do you mean by biased? See, when you say a coin is unbiased or a fair, all the outcomes are equally likely. When you say unbiased, what does it mean, sir? All the outcomes are equally likely. So whatever outcomes are there, every outcome is having equal fair chance. Suppose you roll a die. If it is a fair die, 1, 2, 3, 4, 5, 6, every outcome is having same chance, equal chance, equally likely. So probability of any number is 1 by 6. Suppose you toss a fair coin, head and tail, they have a fair chance. What do you mean by biased or loaded, sir? All outcomes are not equally likely. So for example, if you take a fair coin or a loaded coin, for fair coin, you don't have to mention anything. Obviously, probability of head is 1 by 2, probability of tail is 1 by 2. See, for loaded coin, you cannot directly say, sir, you need to mention what is that biasedness. Okay, sometimes people may say that probability of head is twice that of tail. Okay, probability of head is twice that of tail. So whatever is there, twice that of that is head. That is x plus 2x is total probability 1. That is 3x is 1, means x is what, sir? 1 by 3. So here probability of tail is 1 by 3 and head is 2 by 3. Here what is mentioned, sir? Head is twice likely as tail. So loaded we need to define. Fair coin or fair event we don't have to mention, sir, because all the outcomes are equally likely. But when it is a loaded one or a biased one, we need to mention how that biasedness need to be defined. So generally loaded, we will not just say loaded and ask you to solve it, sir. Okay. For example, you may be having like, head is 0.7 and tail is 0.3. Or you see the Cholet coin where two sides heads are there. Then probability of head is 1 and probability of tail is 0. So these loaded ones or biased ones, we need to define how they are biased. That is in in comparison with one outcome, how likely is the other outcomes. Okay, how they are depending on each other. That particular the biasedness we need to define it. Please note that. Okay, so that is about today's session, my dear friends. So with this we completed the multiplication theorem. So tomorrow we try to take up problems on independent and dependent events, one of the important concepts. Many questions in GATE are from that. Okay. See, starting from conditional probability, multiplication theorem and independent dependent event problem, then comes the Bayes theorem. So after tomorrow, day after tomorrow, we start with Bayes theorem. See, it is not just Bayes theorem for GATE mathematics. For data science and artificial intelligence students, it is one of the machine learning algorithm also. Am I clear? So we'll be doing in that range. So we try to understand things in a more clearer manner, my dear friends. So from here onwards, things get more involved. See, I never say they are difficult, sir. It's not difficult. We just need to understand properly, sir. Okay? Mistakes happens, but you just understand properly, then you can avoid them. See, printing mistakes are different. Conceptual mistakes are different, sir. Okay, printing mistakes I can correct it. For example, today's session, instead of 4 by 52, I written 1 by 52, I understood. I corrected. Conceptual mistake can never be, okay, corrected. So please try to understand these things properly. Then you can answer many questions very, very easily and perfectly. Especially Bayes theorem, there is a lot of chance of doing mistakes. If you understand this conditional probability multiplication, these concepts properly, in Bayes theorem, we hardly do any mistakes. Okay, that's all for today. And tomorrow's session is on problems on independent and dependent events. So we'll close today's session here. Thank you.